that's just, I can't find my overhead that had that on it before, so don't worry about it yet. I must have. Last time we were talking about arcs, and I pointed out that only 1/3 of the heat is transferred to the cathode, and about 2/3 of the heat is transferred to the anode. And we talked about why you'd use straight polarity in gas tungsten arc welding and reverse polarity in gas metal arc welding. I mentioned that Professor Savage had actually measured with a pyrometer moving up a tungsten electrode and found that the hottest spot, if you plot the temperature, was right. Oops, sorry. This thing doesn't always like to stay where it was. Anyway, the hottest spot. So this is 1/3 and 2/3. Okay. So 1/3 goes to the cathode, 2/3 goes to the anode, and the hottest spot here actually is not at the tip. You get electron cooling, and in fact, I remember he used to explain that when you weld aluminum and you're using gas tungsten arc welding, sometimes you will melt off the tungsten tip, and he used to remember seeing rectangular shapes of the tungsten inclusion. Tungsten doesn't melt, doesn't alloy with aluminum significantly because of the difference in melting points and relative solubilities. And the reason, ordinarily, if you see a tungsten inclusion in steel or something on an X-ray, it'll show up as a little ball because you got too hot and you got a drop of tungsten in there. But the reason you get rectangular pieces of tungsten is because you actually melt off the whole tip. I mean, you melt it off back here, and you actually are getting a somewhat rectangular shape in your X-ray image. And he always explained it that way. Then I went through and talked about plasma jets, and we're going to come back to plasma jets. But let me first talk about arc ignition. It turns out arc ignition gets to be a big problem, particularly when you go to robotic welding. And in fact, this is another area where the welding handbook is wrong. If you go to the welding handbook, it will list 4 things for arc ignition, and the 4th one's down here. We'll get to it. The first one's Paschen breakdown. And Paschen breakdown basically says that if I put thousands of volts, or I have a voltage potential of 1,000 volts or several thousand volts, and I bring the 2 electrodes very, very close to each other within like 1/10 of a millimeter, human hair apart, that I'll strike an arc. Now, Paschen breakdown was first discovered back in the 1800s, kind of the mid-1800s, if I remember. And it turns out we now understand that it's not a true phenomenon at all. That's not the physics of it. They actually thought that somehow the high voltage was causing the air to ionize, just a straight DC voltage when you brought things close together. But that's not, it takes thousands of volts, and even though the welding handbook describes this as one of the ways for arc ignition, it can't be because I don't have thousands of volts in a welding power supply, okay? So that doesn't work. Now, field emission, it turns out, is the correct explanation for what Paschen was observing. And field emission basically says if I have thousands of volts and I also bring things very close together, then get this right orientation. I will get a situation. I'm going to focus this if I can, where the high voltage or a high electric field in this case can essentially strip the electrons right out of the metal. Let's go up a little bit. If I'm looking at a energy potential on the surface of a material, so this is the surface of the material, this is out in free space up here, and this is an energy plot. This is the material's work function. So this is the free electron in space, 0 energy. This is an electron up here at higher energy due to the thermal energy of the electrons. And when it enters the material, it drops down to the Fermi energy of the metal in which it's in. I'm sorry, I guess radial distance is going out here, but this is energy level plotted out this way. So if I'm thinking of a free electron in space, there's a potential at the surface. This is the Fermi energy in here, but here's the potential in at the surface. And the electron will, if a free electron's out here in space, it will decay down to this energy level, okay? It's out at this energy level, it drops down here. And that's the work function when it's going into the anode. But when it's coming out of the cathode, it doesn't want to come out of the cathode because it's got this energy barrier, okay? Well, what happens if I apply a very high electric field, I can drop that potential well to something like this, because this is the electric field gradient that I'm going to put on there. Here I have 0 electric field gradient, but if I apply a steep electric field gradient, this is the field coming off the cathode, and essentially the energy barrier, which was equal to the work function before, equals a new smaller work function due to the electric field essentially pulling that potential well down. Does that sort of make sense? And so now the electrons actually have to tunnel through here, which is why when people start talking about how electrons get out of the cathode, they have to start talking about quantum mechanics, because you're talking about electrons tunneling through this potential barrier. If there were no potential barrier, all the electrons would just come out of the metal and go out into free space. Okay, just evaporate out of the metal. Well, it turns out Paschen breakdown, well, let me back up. It takes something on the order of 10 to the 8th volts per centimeter, 100 million volts per centimeter. So if that's a centimeter, take 100 million volts to essentially strip the electrons out of the metal by field emission. Okay, this is called field emission because you got an electric field helping pull the electrons out of the cathode. Well, if I get down to something on the order of 1/10 of a millimeter, so I need 10 to the 8th volts per centimeter, and if I get down to 0.1 centimeters, and how do I do this now? Actually, it's 10 to the 8th volts per meter, I think. 10 to the 8th volts per meter. And so that's 0.01 centimeters is 10 to the minus 4 volts, or 10 to the minus 4 meters. It is, okay, 10 to the 8th volts per meter. And I apply something on the order of 10 to the 3rd volts, some multiple of 10 to the 3rd volts, then I can get, you can see that I can get 10 to the 7th volts per centimeter by getting things very, very close. And if I actually get a little bit closer, and if I have several thousand volts, then essentially field emission, when I get down to something less than a human hair apart, I'm basically using field emission to strip the electrons out of there. It turns out the reason I actually get that extra factor of 10 is the surface of the solid is slightly rough. And the electric field around the tip of one of these little asperities is magnified, okay? If I have a sharp point, I'll get a slight increase in the voltage. So even though this kind of about a human hair thick and 1,000 volts only gives me 10 to the 7th, I might get another factor of 10 from the surface roughness. And in fact, people, if you study and you make a sharper and sharper point, you'll get a higher electric field around that tip, and you can get field emission more readily. And in fact, that's what they do in field emission scanning electron microscopes and stuff. You start with a very, very fine tip to get a higher field gradient to essentially pull the electrons out of there. It turns out we also know that on a liquid surface where you have no asperities, a liquid metal surface, it takes about another factor of 10 in voltage gradient to get field emission from the liquid surface. And in fact, as things get very, very close, sometimes the liquid surface, the electric field actually overcomes part of the surface tension. The surface tension wants to make everything perfectly smooth, and you actually can get little peaks in the metal, in the liquid metal on the surface due to the electric field. So field emission is a real way of initiating an arc, getting electrons to carry the current in the gas, but it doesn't apply to welding, just like Paschen breakdown doesn't apply to welding, because I just don't have that much voltage. My typical open circuit voltage on my power supply is something on the order of 60 to 100 volts, and so that's why I have excess by each of these first two because they just don't work for starting arcs, welding arcs. What does work for starting a welding arc is essentially separation of electrodes initially in contact. And Ragnar Holm was an engineer who wrote a book called Electric Contacts. He was one of these German scientists that was brought back to the United States after World War II, and he worked for Westinghouse. And he and his wife wrote a book, but this was back in the old days when women didn't give credit for things, so it's actually Ragnar Holm's book with assistance from his wife if you read the fine footnotes. Okay, I suspect his wife wrote it, but anyway. He and his wife both worked on electric contacts. Before we go to this, go away from field emission, let me just, since you guys like the stories. I was once brought in by a company up here that made replacement laser cartridges for laser printers. Okay, so it turns out they would machine little aluminum drums, and then they would put a little polymer coating on there. The original Xerox process used selenium as the semiconductive material that you could put an electrostatic charge on, and you could pick up the Xerox toner, okay, or the copy toner. When the copy toner particle is basically just very fine polystyrene with a bunch of soot, basically carbon black in it, and a tremendous amount of energy used in grinding the polystyrene down and mixing it with very, very fine carbon black. And of course, if you have colored toner, you have to, rather than using carbon black, you have to use colored soot, right? Which is just another plastic. Anyway, so you've got this plastic, which is an insulating material, and if you can put an electrostatic charge on some surface, that's what Chester Carlson did when he invented the copying machine, right? You know who Chester Carlson is, right? He was a scientist at Battelle Laboratories in Columbus, Ohio, and he was the guy who built the first copying machine, and then he sold the technology for almost nothing to Xerox Corporation. Okay, and Xerox made a lot of money until they got shown how to do manufacturing by the Japanese. Anyway, what they were having is they were making these toner cartridges, and they were using diamond point machining to get a nice smooth surface on these aluminum drums, which were basically just 1-inch diameter aluminum cylinders. And then they would put a plastic on there. You didn't use selenium anymore. Selenium's got some toxicity problems, and it's more expensive. Now they developed a little polymer film, and these guys used to just dip the aluminum drum in this polymer film, and that would be the electrostatic surface. The polymer was a fairly sophisticated polymer, such that if you shine light on it, it would pick up an electrostatic charge. And there are positive charge copiers, and there are negative charge copiers, and there's lots of technology in these things. So anyway, and they were finding that they were having a problem. They were making their drums, and every time when they would have little dots, always at the same location where they were picking up toner. And if I remember correctly, the layer of the plastic was about 0.01 centimeters, and they had about 600 volts across the little aluminum and polymer interface there. So it wasn't quite 1,000 volts, and they didn't understand why they were getting these little spots each time. Well, it turns out by doing single point diamond machining, it turns out aluminum has always got some inclusions in it, and I said, well, maybe you're getting field emission because you're almost 1,000 volts and you've got a thickness that's on the order, you know, the right type of thickness to get field emission. And all of a sudden the engineer that worked with him says, well, we got these SEM photographs. Actually, maybe he showed me the photographs first. But in these photographs, they had found in some of these spots, they had gone in and cut out the things, and they had found where they had cut into an aluminum oxide inclusion in the aluminum. And it was a very sharp angular inclusion on an atomic scale. Very, very sharp. So it wasn't some just kind of rough machining thing. It was something that was really sharp, and that could explain the extra difference, you know, in these things in terms of the voltage. And in fact, they did have field emission, and all we had to do to prove it is we just did an electroless nickel plate on these things after they machined them, and then put the stuff on. The electroless nickel plate basically buried the oxide inclusions that they had machined over, and all of a sudden the spots went away. Of course, the problem was you couldn't afford to do that because, you know, people's laser cartridge, that cost an extra $1 or so, and the margin on rebuilding laser cartridges was kind of small. So it didn't really solve their problem, but at least we knew what it was. It was field emission. So separation of electrodes initially in contact. This is what usually happens when a welder, a manual welder, is welding. They've got the welding electrode, and they come in, and you've got your hood and everything, and you just gently strike the surface and pull it away. And the way that works is if I have two asperities and they come into contact and then I pull them apart, as I separate them, the resistance goes from a low resistance to a very high resistance. And there will be some current as I first touch, even though I only have about 2 or 3 volts, or actually I have about 60 volts, but even with only 2 or 3 volts, there's enough current going through here. As the resistance goes from the low value to the high value, you get to some optimum resistance in between where there's enough power to essentially vaporize these surfaces. And it turns out, Ragnar Holm worked it out such that it turns out, if you idealize this geometry, and you say this is the interface temperature T theta, and you have some voltage V0 over 2, plus V0 over 2, minus V0 over 2, and you have some ambient temperature, room temperature, you can work out an equation that relates the voltage to the thermal energy, okay? Electron volts are equal to the thermal energy. There's a relationship in here between the thermal conductivity of the material and the electrical resistivity of the material. It turns out you're solving Laplace's equation, and basically the voltage isopotentials in here look exactly like the temperature isotherms. It's just solving the potential equation in here. We won't solve it. But you end up with this equivalence between voltage and temperature. And it turns out for different materials, like for copper, the melting voltage is 0.41 volts. You now have this equation that relates temperature at the interface, and the melting point of copper is 1083 centigrade. The melting point of tungsten is 3300. Turns out the melting voltage of tungsten is only about 1.1 volts. And you can talk about a boiling voltage, if you will, and a boiling voltage of copper, maybe in my notes. The boiling voltages are also extremely high, or extremely low. The boiling voltage of copper is 0.8, and the boiling voltage of tungsten is 2.1. So I can boil tungsten. If I get tungsten or copper, I have enough energy in here to basically ionize that gap. And once I get free electrons in there, then that will create the plasma that starts the arc. So separation of electrodes initially in contact is, in fact, one of the ways that we start arcs. And the last one is high frequency. If I apply an electric field, an RF field on the order of 100 kilohertz, I basically can, and I bring things reasonably close together, I can oscillate essentially the electrons on that atom such that some of them will ionize the atom. And you may have seen that if you've ever seen a Tesla coil in high school physics. You ever see a Tesla coil? You take a Tesla coil at which is an RF field, and you bring it up to a fluorescent light, and the fluorescent light's not even on, not connected to anything, and you'll see it start to glow. Okay, so without electrical contacts, just high frequency, you can basically get the gas in the fluorescent light to ionize, which is the glow, and so you get a glow discharge from that. We use the last two, touch starting and high frequency, to start electric arcs, and it's important for robots because robots don't have the manual dexterity to come in and make a nice, soft touch. they kind of come in and bang, right? They don't know exactly where the material is. And ordinarily, you kind of, a real welder comes in at an angle like this and kind of scratches it across the surface. But robots would hit it too hard. I remember in one robotic welding system for pressure vessels I saw in Japan years ago, they basically, in order to get the arc to start, they would, for the robot, it's robotic welding is a system, and they essentially, when you finish welding, you would have, by surface tension, you form a little drop on here. So this might be a 1/16 of an inch in diameter, which is 1.5 millimeters or so. And remember, surface tension is going to form a ball that's going to be something on the order, and for anything, it's going to be fairly spherical for anything less than about 3 millimeters in diameter by surface tension. So you get a little ball on the tip, and that tends to be hot. And if you don't keep the shielding gas on this, this will oxidize. An oxide layer is going to prevent the thing from drawing a current when you touch, and you can't do a touch start. So in order to make the robotic welding system work, it was just a great big cell about half the size of this room, and they were welding nozzles on pressure vessels that were, 4 inches thick and stuff. And basically, the gas metal arc wire feed, when the arc had stopped and then they wanted to start again, it would go over to this one thing on a post on the side of the robotic welding cell, and there was a little plate there, and the welding torch would be brought over. The wire would come down until it would just feel it touch, and then some little clippers would come out and clip the wire off and make a chisel point. So they would cut this off, which you don't want, and they would end up with a little chisel point like this. And then when they come back over to where they wanted to weld, they would drive that wire in, and they'd have enough voltage on there so that when the chisel point touches, you'd have enough current that you just blow that thing apart. Okay? It's just a sharp point, and you blow it apart, and that's how you get arc starting. Now, it turns out that was almost 20 years ago. That was one way to do it. Nowadays, with sophisticated power supplies in robotic welding systems, you actually can use this same electromagnetic pinch effect that we talked about before, the Lorentz force, where you have a squeezing force on the drop. When you stop welding with the robot, you basically will come along, you may be running at a 200 amperes, and you don't know it, but when you tell the power supply to stop, it actually puts a pulse of like 500 amps through the whole thing. And that 500 amps essentially squeezes the drop off so that you don't get this great big drop of molten metal on there. You essentially neck it down so you get something, it might have been molten, but it's somewhat pointed because you basically just squeeze the drop off. Okay, sort of like milking a cow if you want. Okay, just squeeze the drop out.
When you, the robots are welding, do they still get that roll of dimes on the bead?
Roll of dimes on the bead. Oh, you mean the nice pattern across there? Okay, the roll. No, they don't. They'll be nice and usually they'll be nice and smooth because they've already optimized that they're going at a constant speed. The roll of dimes you're talking about is because the manual welder, in order to control the speed, is circling. Okay, and that's how he produces this ripple pattern on the surface. And a good welder will make a perfect spacing. I mean, it's just amazing to me how uniform that spacing is on the roll of dimes. And by roll of dimes, what he means is if you took a roll of dimes and lay them out sideways so that they're kind of at an angle to each other, you'd have a surface with these little ridges on there. And yeah, I don't know. I probably have something in my office that's got the kind of roll of dimes from a manual weld, but I've seen it, and it's just a good welder. It's amazing what they can do. But no, a robot doesn't do that because a robot usually is just going constant speed. So you just get everything uniform.
Like how far to keep the electrode off the surface?
Okay. You usually have voltage feedback.
Oh,
okay. Or current feedback. It turns out when we get to gas metal arc welding, we may talk about it, but it's sort of self-regulating. If you drive the electrode in closer to the metal, it draws, well, you have a power supply that will, well, if you drive it in too fast, it will stick, it'll stub out. And if, depending on the inductance in your power supply, if you don't have very much, well, if you have a lot of inductance, you can't change the current enough, and the power drops and everything freezes, and it's stuck, and you gotta turn your power supply off and cut the wire and grind out the defect. If you got, if you don't have very much inductance in your power supply, when you stub out like that, your power supply voltage and current may go shooting way up, and you may blow the thing apart, okay, which also can produce a defect. What you really want is the wire feed speed and the right amount of inductance, such that as you drive the electrode in closer, you get a shorter arc, and that means that it wants to draw more current. As it draws more current, you're going to get more melting of the electrode, so the electrode melts back. And if it goes back the other way, then you're getting less power, you got a longer arc, and so more of your voltage is controlled by, just in the plasma column rather than the melting of the tip of the electrode. And so what you really want is what they call slope to the power supply. If you look at the voltage current trace on the power supply, this is your open circuit voltage, and you want enough slope such that you will have a stable operating point. If you move closer, your voltage decreases, your current goes up, and you melt the electrode back. If you pull back, then you have more voltage but less current, and since current's what's doing the melting, you melt a little slower, and the thing always wants to come back. You have a stable point, it always wants to come back to the operating point. In fact, that's what you do. That's why you can have this kind of constant wire feed, and you can have a human whose motion is not perfect because there's a self-stabilization, provided you have the right voltage slope. So typical, in the old days, they used to have slope voltage inductance, SVI power supplies. Okay, you could change your slope, you could adjust your voltage, and the I didn't stand for current, it stood for inductance. And sometimes you could change the inductance, but usually there was a fixed value that the power supply manufacturer had found was enough inductance in the system. So you got a dynamic system, and you basically set up something that's self-regulating. Okay. Nowadays, well, actually, now that we go to inverter power supplies, they have almost no inductance. There's no great big heavy inductor. I mean, the inductors in the old transformer regulator power supplies might have weighed 200 pounds of copper, because you got, if you're talking a 500 amp power supply, you got to have some pretty heavy cable to make this magnetic field. You got to have enough turns, and this thing was a big heavy inductor. And with the new electronic power supplies, they basically program in the inductance. Okay, it's artificial inductance. It's not true inductance of stored magnetic field, but the program won't let you change the current but so fast. Okay, so you don't want to change the current too rapidly. You want to, so you're dampening the system here, and the slope is providing your self-regulation, and the voltage is controlling the power. So there's a lot of stuff in welding power supplies. It's not, you can't just plug into 110 volts and strike an arc and weld with 110 volts, okay? Because there's nothing to control and self-regulate the circuit, okay? So anyway, that probably more than answers your question, right?
So what does one of those graphs look like for, you said you can't do the straight 110 volt supply, what's the difference in
the straight 110 doesn't have any slope. It goes out here until it blows a fuse, okay, usually. Depends on what else is in the circuit. Now, if I have some motors in the circuit, motors provide inductance, and that they also will provide some internal resistance, and they may provide enough slope, but most 110 volt circuits don't have enough of this dampening capacity or the slope to do self-regulation. They just pull out power no matter what. And that's on 110, where you realize if a 15 amp circuit at 110 blows a fuse, you know, if you just kind of short something out accidentally, you realize you actually probably drew somewhere between 100 and 200 amps for a fraction of a second. Okay, it doesn't trip at 15 amps. In fact, it'll probably take minutes at 17 or 18 amps before the circuit breaker will know that it's got too much power going through it. Okay, it's usually those dead shorts that you want to break, within a fraction of a second. And in those cases, you will spike the current to a couple of hundred amps. You wouldn't want to do something like that with a welding power supply because the problem with welding power supplies is, I always tell students, they don't trip fuses. Okay, you've got them fused with enough power behind them that you can get 1,000 or 2,000 amps out of them if you go to a dead short. And so they don't trip fuses, and you can start fires with them and things like that. Ordinarily, you have fuses on a regular power supply. Now, it gets really interesting when you have something. There's a case situation down here in Rhode Island where you were right next to the power company substation, and they had 13,800 volts lines, and they had them spliced together, and the splice broke. And most of those high voltage lines up there are not insulated. They don't put rubber or anything on them. They're just bare. Okay? In fact, you ought to be careful of the cables coming into your house. Most of those are insulated, but some locations, the cables up there more than 15 or 20 feet in the air are not insulated. Okay? So you shouldn't, if you got metal ladders or something and you touch one of those, you'll probably die. Okay. Anyway, so what happened is this place in Rhode Island is an old next to the substation, and next to the substation you got lots of power, and the fuses probably aren't going to trip. Actually, it's vacuum circuit breakers. But the circuit breakers probably won't trip till like 40,000 amps or something. And one of these things, cable fell to the sidewalk and started arcing along the concrete. And there was enough resistance in the concrete, because concrete's not a good conductor, right? That basically enough power was going into the ground started heating, and the building next to it, you now have 13,800 volts on the sidewalk, and that's all got to be dissipated, right, into the surroundings. Well, the surroundings happened to be right next to the sidewalk was this brick wall of this old mill building, and supposedly it had some file cabinets up against the wall, and there was arcing going on between the wall inside the building and the file cabinets. And this eventually started a fire. Okay, actually, initially when it hit the ground, the 13,800 volt cable hit the ground, it was blowing sparks around, and it actually caught some grass across the street on fire. I mean, there's a nice fireworks display going on, but there's not tripping any circuit breakers because you're right at the substation. You got lots of power, okay, and it's not designed to just trip when you draw a little more power, right? And so this thing, by the time the fire department got there, they thought it had just started a fire over here, and they didn't realize that there was a fire going on inside this building in the storeroom with the file cabinets. So they were over here putting out the grass fire, and of course they had called up the power company and have them shut the power down, which is not something you do right away. On a 13,800 volt system, you actually have to get into the switch yard and shut it down. And they shut the power down. Of course, the firemen weren't going to do anything over there near the sidewalk where the 13,800 volts was alive until that. But as they put the fire out and the power goes off on the line, the fire had already started inside the building, and the firemen start seeing smoke coming out of the building. And it was down the basement. Anyway, it did burn down the whole mill building. It's $40 million worth of damage. But you got to remember, big power systems. I mean, your wall outlet trips fuses, but big power systems don't trip fuses. They just pump the power. Okay, so it gets to be pretty exciting sometimes. So anyway, let me go back to finish up this. So you squeeze off. You put a pulse of current in. If you were plotting the current versus time, you're running along at a few hundred amps, and you tell the machine to stop, and it doesn't just drop the current. It gives a huge pulse, and then it drops the current. Okay, and that huge pulse knocks the last liquid drop off there, leaves a little bit of liquid, but hopefully leaves a little bit of a point, and you keep your shielding gas going long enough to let this thing cool down and solidify without a heavy oxide. And now you don't have to go and cut the thing off like the Japanese did 20 years ago with the fancier power supplies. The robot can just go in and push that little tip that sharp tip of molten metal into the workpiece and hopefully start an arc. Okay? And in fact, if it doesn't on a regular basis, you probably need to go in and check the electronic circuit on your power supply to make sure it does. The other thing we do is on gas tungsten arc welding power supplies, they actually have a high frequency overlay. So you can either use touch start, which is this type of stuff, or you can use the high frequency, 100 kilohertz overlay. And basically, you have a couple little arc gaps if you go in the power supply down in the weld lab, and you have to adjust these, and you have to change them every now and then. If you're running 200 or 300 amps, you actually have the current going across this little arc gap within the power supply, and it's some of them, if the power supply is water cooled, most of them are air cooled, and these gaps wear out. But you're basically allowing the arc to go across the gap. You got some magnetic fields that you put in there, some magnets in there, to help create a high frequency on top of your couple of hundred amps. So you got a very high, you got a couple of hundred kilohertz ripple, and if you turn on the power supply and you have a regular old radio going, you're going to hear a bunch of crackling going on because all of a sudden you've got a stronger radiator than the radio station, at least close by. You actually have on these things, you can either run the RF current continuous through the whole weld if you're doing AC, or you can just do it for the first 5 or 10 seconds, and sometimes they'll have a little adjustment on there. So you get the, for the initiation of the arc, you have the high frequency to help you initiate the arc, because you don't want to have to touch your tungsten into the workpiece, and that'll mess up the tungsten tip. So arc starting is not as trivial as you might think in welding power supplies. It gets to be a problem, particularly with robotic welding, but we essentially have resolved that in recent years. Okay, let's go back to plasma jets and what we do with arc pressure. We talked about the fact that the plasma jet drives flow in here, and I think I said 500 miles an hour. It's actually 500 meters per second, which is faster than 500 miles an hour. This would be supersonic flow if it were not a rarefied gas. If this were, the density of gas at room temperature, it would be supersonic. In fact, it's not supersonic. In fact, that's probably one of the things that helps limit it. But nonetheless, it goes, as we said before, as the square of the current density, which the current density goes as the square of the current because the arcs don't change that much in size. And so as a result, if you were to plot the pressure in this arc of this jet hitting the surface versus current, you'll get a parabola that increases like that. So this is the arc pressure, and it turns out if you look at that, can do several things. It can depress the weld pool surface. Remember I told you about how you depress the central artery. You have Michael Dukakis talk to it for an hour, right? That's where we finish up the last time. Well, I've got a molten weld pool surface, and where do I? Well, let's do it up here. And I could have something that looks like this, where the molten surface of the weld pool may be depressed about 1 millimeter, or I could have one depressed 10 millimeters. If you actually go out here, you'll find if I were to plot the surface depression versus current, it actually kind of goes like this, such that at about 250 amperes, somewhere around there, plus or minus 20 amps, I actually get enough surface depression that I actually start drilling a hole about 5 millimeters deep into the weld pool. So this would be about 1 millimeter, and this is about 5 millimeters. The whole process of this surface, actually, it probably follows this pretty well up to about 1 millimeter. And then it jumps over just 20 or 30 amp range to about 5 millimeters and actually starts gouging through the surface. Now, when I start gouging through the surface, I'm going to get a significant increase in the penetration of the weld, the size and depth of the weld pool. But in addition, I end up changing from a nice uniform smooth running weld, which on a robot doesn't have the little dimes, okay, stack of dimes, but on a manual weld with someone operating it, you actually get kind of waves washing up on the shore, and that's what gives you the little stack of dimes, okay, as they oscillate around on this. If I get to 250 amps, it turns out that I will start digging down into the surface, and as I do that, I start producing lots of different types of defects. Okay, I like to liken it to a motorboat going through the water. If you look at it, and so you got the water is your liquid, and the boat is the thing that's depressing the surface of the liquid, and as it moves through there, it leaves a wake behind it. Okay, and if you look at that wake, because of Bernoulli, you've got rapid motion of the liquid going around the sides, which as it comes together in the back, and the stuff comes to stagnant flow, you get something raised up against above the layer of the average layer of the lake or the water. In other places, you'll get a depression, and you get this complex shape behind the whole thing. Well, if that stuff starts getting into the solidification range of the weld pool, I start producing undercutting, which is a little notch at the side of the weld bead. Okay, an undercut would show up as a little depression right here. Well, actually, it's going to end up showing up right here, where I basically freeze in part of the wake where I have a depression. Okay, if my combination of travel speed and current and everything is just wrong, okay, I have just the wrong combination, then I'll freeze in an undercut, and that undercut's going to have to be ground out if it's more than about a ½ millimeter deep. Okay. What was the undercut? Oh, I had a pipeline failure in Texas where they were doing submerged arc welding in the pipe mill, and the undercut was only about a ½ millimeter, but the code only allows about a ¼ millimeter, because it turns out the pipelines change the pressure and you get a fatigue crack. And this thing had been in service for over 20 years, and it finally developed a fatigue crack at this thing. There was some corrosion going on too, which is what the fight was all about. But it finally split open and let go 16,000 gallons of gasoline into this farmer's field. Okay, actually a rancher in Texas, right? So the cows didn't like to drink the water, and the EPA was all upset and everything else. But that was because of an undercut that was not caught by the inspections that they were doing at the steel mill. So plasma jets affect defects in the weld. They also affect overhead welding. We talked about that. Yep.
How would you detect said undercut? Is it visible, or is it something you would have to?
The best way is visible. It turns out when they were making this pipe in the 1960s, they actually this is pressure pipe for oil wells and stuff. They were actually piping gasoline, and in fact, if you went back 6 or 7 years ago, they had a real problem with supplying gasoline because this pipeline was 28 inches in diameter, and it was pumping gasoline from Texas to Chicago. Okay, so the Midwest, it was supplying much of the gasoline that was used in the Midwest of the United States. And when this pipeline failed for a couple of months, they had a problem supplying gas. They had to barge it up the Mississippi and everything else. And, a 28-inch diameter pipeline running at 900 psi can, actually maybe it was only 700 psi, but can pump a lot of gas. Okay, takes a lot of barges to replace that.
That runs the entire length of the country.
Well, from Texas to that's that direction of the country, yeah. But I mean, I can't remember what the number is. I can't remember if it's 30,000 miles or 300,000 miles of pipeline greater than, I think it's maybe 30,000 miles of pipeline more than 12 inches in the diameter in the United States, which is the highest density of any part of the world. Not too surprising. Although, if you looked at one little small area, I'm sure there might be parts of the Middle East where have more pipes, large diameter pipes. But actually, I just saw something, what was it, that had the piping in the Gulf of Mexico. Okay, now these are a lot smaller pipes. Some of these might be, 6 or 8 inch, because any given well, may not be producing that much. But it just, it's just a checkerboard pattern on about a 10-mile basis. It's just pipes all over the Gulf of Mexico. Anyway, So your question was, oh, how do you detect it? They had continuous radiography, okay, with a fluoroscope. So they were taking a picture of the weld. However, in the other part of the course, we talk about non-destructive evaluation. Turns out you've already got a change in shape. You got the weld reinforcement, and so it's hard to see right there where it stops the change in density of a 20 thousandths flaw in something that's 280 thousandths thick in this case. Okay, so it's hard to see it. Someone's supposed to be doing a visual inspection, but how'd you like to be the guy who for 8 hours a day is supposed to be watching this pipe come through there? Okay, and it's coming through continuously, and you got to watch this thing for 8 hours a day. Well, obviously people tend to fall asleep and or lose their attention span when your job is that exciting, right? And so some of this stuff got through. Okay, so X-rays are the primary. Well, X-rays are the first thing, and then visual inspection. And there are several people who should have caught it on visual inspection, but so what? Sometimes things get through. That's one of the reasons you have failures. Okay, because people missed it. So the arc pressure depresses the surface of the weld pool, can lead to all kinds of deformation and of the weld pool and defect formation. It also allows us to weld out of position. It pushes the drops up against things. What else does it do? Oh, it contributes to arc stiffness and prevents arc blow. It turns out that you want the arc to be relatively stiff. If a small breeze comes by, you don't want it to blow out the arc. I mean, you can blow out a candle with a small breeze of a few miles an hour. You'd like the welding arc to remain in position doing the heating where you want it in a 5 or 10 mile an hour breeze. If you have more than a 5 or 10 mile an hour breeze, you've got to have shielding curtains to keep the wind out of the welding area. And so it's not, if you see someone welding outdoors and they have curtains around the welding, it's not just to protect other people from the radiation. It's to protect the weld from the wind blowing by and blowing the arc away, because you can get a defect. Now there's other things that can blow the arc away. One's magnetic arc blow, and actually I may have I don't see it right now. Magnetic arc blow if I have a welding electrode, and here's my workpiece down here, and the current is going to come down here, and the plate is here, and I'm going to have some ground location over here. So this is the current path. And it goes down here. Whenever the current turns a corner, there's a higher magnetic field, or there's a concentrated magnetic field. The magnetic field is uniform around here, but if I draw my circles here, you can see I have less density on this side, on the outside of the curve, and I have more density of the magnetic field on the inside of the curve. Okay, it's just, if you had little circular rings on here and you bent a spring, the spring would be more dense here than it is out here. Okay, well, what the arc doesn't like high magnetic fields. It will try to blow away from that, and so in fact there will be a force on this thing blowing it in that direction. And it turns out the magnetic arc force is not such that you have to worry about it too much if we're talking about something less than the 500 amps. But if I get up to several thousand amps, then I actually have high enough magnetic fields to just blow that arc away. Okay, 50 Gauss magnetic field will destroy a weld. So it turns out one of the problems with steel sometimes, and it turns out HY130 has this because it's a high nickel steel and it's easily magnetized. It will essentially, the steel can magnetize itself and generate enough magnetic field that you can't weld. I remember once at David Taylor, I was down there one summer, and they had been the welders had been trying for several weeks to weld this one HY130 plate, and they had gone in, they demagnetized the plate, they did all kinds of things, but they still had enough residual magnetism that they would run the arc. You know, they would try, actually they're doing it manually, they would try to run the arc down there, but it would just blow away, no matter what they did. You don't usually run into that big a problem at the currents that we're dealing with, but at high current and in certain types of easily magnetized steels, it can be a big problem. Okay, we'll see you again tomorrow.